Hey everybody, we're back from spring break. I'm not really sure what that means, but we're back. Today we're going to introduce the probability chapter. Now, probability is probably something that you think of when you start getting into problems. What is the probability of this happening? You know, there's a 70% chance of rain today, that sort of thing. That's what you think of. And usually that's exactly what we're doing. However, probability goes way deeper than that, and you can't know what the probability is of something happening if you don't know how many different ways the event can occur. Okay, I know that's kind of a confusing thought, so let me just use the lottery example. What is the probability of you winning the lottery? Well, you can't know the probability of winning the lottery unless you know how many different ways those little white balls can come out of the machine. It turns out, spoiler alert, there's like 292 million different ways that the balls can come out of the machine. So that means your probability of winning the lottery is like 1 in 290 million. So today's lesson isn't really going to feel like you're talking about probability, because all you're really talking about is how many different ways something can happen. And that's okay, because we have to build the foundation. So this chapter is going to feel backwards, and that's fine with me. We're going to build it up, we're going to get the job done, and then when you're ready, that's when we'll start talking about what is the actual probability, what are the actual chances of something occurring. Now, the first part of this chapter is called the fundamental counting principle. And I always find it to be absolutely hilarious because this is the easiest thing we do arguably in the entire geometry class, but it also has the hardest name. You know, we talk about lots of difficult concepts that have easy names. Now we're talking about an easy concept that has a hard name. So let's say you couldn't decide between outfits. You had 3 different shirts you couldn't decide on. They matched well with 2 of your pairs of jeans, and there were 3 different pairs of shoes that went with the whole thing. Now, they actually put this type of question on the ACT, just so you know. It seems like it's really intimidating because it's a word problem, and some of you just aren't real fans of word problems. You've got shirts, you've got jeans, and then you can't decide what pair of shoes you're going to wear. How many ways could you dress yourself this morning or afternoon or whenever it is you're reading this? All you have to do is take the number of options you have for each category, and then when you're done, multiply those numbers together. So let's say you have 3 different shirts you're thinking about wearing. You have 2 different pairs of jeans. You have 3 different pairs of shoes. All you have to do, 3 times 2 times 3. 3 times 2 is 6. 6 times 3 is 18. There are 18 ways that you can dress yourself this morning. That's it. All right. Now, I know a lot of people are postponing weddings and that sort of thing, but this next question makes me think about weddings. Because a lot of times at a wedding, you know, you'll have a couple of different choices of entree and that sort of thing. So if you have a choice of 2 entrees, 2 sides, and 3 desserts, how many different options do you have all together? All right, so let's say, and we'll just make a list here. Let's say you're choosing between the chicken and the steak. All right, now we're talking about 2 different sides. It's always fun to think of different things that you could throw in here. It's always fun when you're teaching this live. Obviously, we can't do that, but that's okay. Let's say you're choosing between the green beans. My wife cooks them with bacon. You got to do the bacon. You cook something with bacon, everything tastes like bacon. It's fantastic. Or the potatoes. And then as far as the desserts are concerned, let's say you are choosing between cake and pie and brownies. It doesn't really matter. This is all just an illustration. You have 2 different choices of entree. You have 2 different choices of side. You have 3 different choices of dessert. 2 times 2 times 3 means you have 12 different options. Now, if you're wondering why I went out of my way to choose different types of food and that sort of thing, we're going to draw this out here in just 1 second. So I really do have a reason why. I didn't just do it for no reason. All right. So I wanted you to actually write out the words fundamental counting principle. Mostly because I don't want this to be the kind of thing that you get so intimidated about the name of that you just don't bother doing it. Because again, it's one of the easiest things we ever do in math class. Now, this method is what you use when your events are independent. Okay, independent events are events where one of them has no effect on the other. So it's not like you go to a restaurant and you order the pasta and then they say, oh, you ordered the pasta. That means you're not allowed to get this dessert. Your choice of entree and your choice of dessert are completely unrelated. You are allowed to do whatever entree you want, whatever dessert you want. They are unrelated. They are independent of each other. Okay, so the fundamental counting principle is what you use when your events are independent. Now, we'll get into dependent events later, but right now we're just going to start with this method. Now, in case you haven't picked up how it works, you count your options for each category, and then you multiply the numbers. That is all you do. Now, when it comes to a tree diagram, this is where you have to actually draw things out. And when you're done, you count your options that you drew. Now, I'm going to abbreviate chicken and steak here, just like I want you to do on your paper. Okay? Because if we don't abbreviate, things are going to get really, really messy. All right. So I want you to draw out. These are your options. Okay. You can choose between chicken and steak. Now, we talked about how you could either get green beans with bacon, I hope, or you can get potatoes. Now, if you're at a good wedding, you can get both, but that's another story entirely. All right, so what we're doing with a tree diagram is we're tracing our options. So you can get an order of chicken with green beans, or you could get chicken with potatoes, or you could get steak with green beans, or you could get steak with potatoes. So basically a tree diagram is when you are just tracing every single thing that could happen. Now at the end, this last one that we're going to do is going to have 3 different branches coming off of it, because we talked about how we had 3 different choices for dessert. So at this point, our tree diagram is going to get a little bit funky, because we now have a little bit more to draw. Now we're talking about 3 different options for dessert. Now the correct answer for dessert is cheesecake, but I didn't want to overcomplicate things, so we'll just use cake or pie or brownies. Okay. So if you follow each individual branch, it demonstrates an individual choice of meal. So let me actually label this out, and then you'll sort of see what I mean by this. Every path represents a different meal. So let's say you chose, and I'm just making this up as I go along, let's just say you chose this path right here. That would be somebody who ordered steak with green beans and had a brownie for dessert. Let's say you chose this pathway right here. This would be somebody who had chicken with potatoes and a piece of pie. Okay? Now, the significance of a tree diagram, other than being able to look at all of the different ways something can happen, is that you can also tell how many different ways something can be done. It is actually a visual example of the fundamental counting principle. Because if you look at all the branches at the end, if you look at all the different options at the end, so that would be 1, 2, 3, 4, 5, 6, you get the idea, 7, 8, 9, 10, 11, 12. If you look at the end, you found out that there are 12 different options that something can be done. If that number looks familiar, it's because it is familiar. That's exactly what we had earlier. So a tree diagram is really just a visual representation of what we already knew. Okay. All right. Now, I always throw in the license plate problem with the really big answer. I throw that in because of my time in Arizona. Back in the day, license plates in the state of Arizona had 3 letters followed by 3 numbers. How many license plates could be created using this system, and why do you think they changed the system? Now, we're not going to do a tree diagram. That would be insane. We're not talking about, oh, we're just going to list off the different possibilities for each thing. That would take way too long. What we're going to do instead is we are going to try to break this thing down and figure out the answer just by multiplying instead. So if you think about how many different ways you can make a license plate, if you know it's going to start with a letter, you have 26 different options for what letter to choose. And then your next choice has 26 different options. It's almost like each letter is its own category. Okay, so if you're wondering where these numbers are coming from, that's what's happening here. All right, so you got 26, 26, 26. Now, the license plate is then going to have 3 numbers in it. Now, when you think of numbers, a lot of people, their first instinct is to write down 9. Oh, well, there are 9 different possibilities for numbers. But if you think about a keypad, there are actually 10 different possible digits that you could put in a spot, because you could go from 0 to 9. So we're actually going to then go 10 and 10 and 10. So when you think about how many different ways using that format that you could come up with a license plate, you would actually get 26 times 26 times 26 times 10 times 10 times 10. That is how many different license plates you could come up with. 17,576,000 plates. Now that seems like a lot of license plates. Why would you have to change the system if you have 17 million different options? Well, back in the day, like I was saying, you would get a new license plate every time you got a new car. And so in the case of Arizona, let's say there are 7, 8 million people in the state of Arizona. I think it's 8 or 9 now. If every person had a couple of different license plates, suddenly now you start to run out of plates. And so you have to change the system that you use to make a license plate, because otherwise you're going to get a repeat, which defeats the purpose of having your own license plate. All right. Let's do these pin number problems real quick so that you can wrap this page up and go on to the back. So how many different 4-digit pins can be made? Well, if you think about the fundamental counting principle, again, in a pin number, every digit of the pin number is sort of its own category. You know, every time you choose a digit for your pin number, you know, it sort of resets before you move on to the next one. You have 10 possibilities for the first number, for the first digit, I should say. Then 10 possibilities for the second one. 10 possibilities for the third one. And then 10 for the fourth. Every choice of digit is independent of the other one. So when you think about how many different 4-digit pins can be made, there are 10,000 different possibilities. Okay? Now, let's throw a little curveball at you. What would happen if you knew that each digit was odd? Well, now suddenly you don't have nearly as many options. Now, it's going to be real tempting to say, oh, you only have half as many options. Well, what actually happens is you only have half as many options for each digit. So instead of doing 10 times 10 times 10 times 10, you're actually doing 5 times 5 times 5 times 5, which is actually only 625 pin numbers. So if you have a pin number and every digit is odd, you've actually taken the number of possibilities that you have and you've actually cut it down 16 times less. You have 16 times fewer possibilities. It's pretty shocking to think of, but it's the way it goes. So if you tell someone, hey, you know, my pin number is all odd, which I don't know why you would ever do that, but if every digit was odd, then they would have a much better chance of narrowing it down. That's why you wouldn't do that. All right. How many 7-digit phone numbers can be made if the first digit cannot be 0 or 1? In case you didn't know that, your first digit in your phone number cannot be a 0 or a 1. So when you think about how many 7-digit phone numbers can be made, you have to consider that. The first digit can't be a 0 or a 1, which means the first digit could be maybe a 2, 3, 4, 5, 6, 7, 8, or 9. So you have 8 different options for the first digit and the second digit. Now, as soon as you make it to the third digit on, it doesn't matter which one you choose. So there would be 10 different possibilities for each of those. So you take those numbers, you multiply them out. And it looks to me like what you're going to get here, 8 times 8 times 10 times 10 times 10 times 10 times 10. Whew, there you go. Now, I guess that brings up a really good question. Why do we have area codes? Well, there's a certain point where your area, your city, your state, your whatever runs out of phone numbers. You only have 6 million choices. We have 320 million people in the United States, so it only makes sense that you would eventually have to have different area codes. Not that you ever really ask that question maybe, but that is the breakdown. All right, so turn to the back. We're going to go through the back real quick, and we're not going to change much. We're going to learn a new concept, and it's called permutations, but it's not going to change much. It's a lot like what we did before. We're still going to break things down into categories and then multiply numbers together. The only exception is the numbers in the blanks go down every time. As in, the events are dependent. One event depends on the other one. As soon as you choose something, you can't choose it again. Okay, so let me show you an example of a situation where you would need to use permutations. So let's start with a band. So let's say you've got a band that you really like, and they are opening for another band. So they only get to play 3 songs. Maybe that's just the way it's going to go down at the concert here. They have 5 popular songs. How many different ways can they order the songs they choose? Well, they have 5, but they only get to play 3 of them. So I want you to pay close attention to what happens here and why this is different. This time, if you think about how many different ways they can choose a song, they have 5 different ways that they can choose what song to play first. But as soon as you've played that song, you're not going to play it again. So they don't have 5 choices anymore when they get to their second song. They only have 4. And then as soon as they've played that song, now they only have 3 choices left for their third song. So that's the difference between what we did earlier, which is just multiplying different things together, and permutations. In a permutation, the number in the blank goes down by 1 every time. So the answer to the band question is 60 waves. So again, this is what you do in the case of dependent events, as in as soon as one event happens, it cannot happen again. There are no repeats. Okay, so question number 2. 10 people enter in an essay contest. How many ways can first, second, and third place be chosen? Well, you've got 10 different people who could win the essay contest. But as soon as somebody wins the contest, they can't finish second also. So let's say somebody finishes first. Well, now you only have 9 people left who could finish second. And then you only have 8 people left who could finish third. Because as soon as you have chosen first and second, there are only 8 people left. Okay, so you multiply those numbers together, you get 10 times 9, which is 90. 90 times 8, which is 720 ways. So again, what's happening here is as soon as something is chosen, it cannot be chosen again. So that's how permutations work. Okay. How many ways can you rearrange the letters in the word tire? So basically, we're taking each letter and we're just scrambling up the letters. Right, there you go, like a rite of passage. I'm just making stuff up. These don't have to actually be words. There you go. Terry, whatever, it doesn't really matter. How many different ways can you rearrange the letters in the word tire? Well, it actually fits in to the same lesson that we just talked about with permutations. You have 4 letters that you can choose from to put first. But as soon as you have placed a letter down, now you only have 3 choices for the second, and 2 choices for the third, and the last letter is the only one you have left. So how many ways can you rearrange the letters? 4 times 3 times 2 times 1 is 24 ways. Okay, so there you go. 4 times 3 times 2 times 1, 24 looks good to me. Now, because this comes up so much, your calculator actually does these. Now, you're going to have to sort of find this for yourself or do the formula by hand. Most calculators have a way of doing probability. Some of them actually have a PROB button. Some of them you have to go into different math categories and dig out probabilities. Maybe tomorrow I'll explore for you and I'll help you figure out where to find it depending on what type of calculator you have. But these come up enough that your calculator actually offers you a formula for how to do permutations. So it looks like this. Now when you see this right here, that is actually the way to set up the formula. Okay? That big P stands for permutations. The little n is how many items or things or whatever you have to choose from. Okay. R is how many of them you're actually choosing. Okay. So if you had done that band problem from earlier, that would have been a 5 P3. Because you had 5 songs to choose from and you were choosing 3. So the band problem you did earlier would have been a 5P3. All right. Now, if you look in the formula, you're going to see a couple of weird exclamation points. I don't know if you've ever done that in math. It doesn't mean your number is angry. It's used in what are called factorials. And a factorial is when you start with a number, you count down, and you multiply. So for instance, if somebody asked you what 7 factorial was, you would do 7 times 6 times 5 times 4 times 3 times 2 times 1. Now these numbers start getting really, really big. You know, for instance, 7 factorial is 5,040. Now, if you're doing like 3 factorial, it's not a big deal because it's just 3 times 2 times 1, which would be 6. I mean, so it's not like it has to be big, but the numbers overall, they start getting really, really big really quick. Here's just an example in between. 5 factorial would be 5 times 4 times 3 times 2 times 1, which would be 120. Okay? That's what a factorial is. Now, I'm going to do a demonstration of a problem 2 different ways so that you can see where I'm coming from here. And we're going to do it once with the formula, and we're going to do it once the way we've done it with blanks. All right, 6 people want to run in the senior class election, and there are 4 positions available: president, vice president, treasurer, and secretary. So I'm going to make 4 different blanks. And there are 6 different people that want to run. So that means there are 6 different people who could become senior class president. I don't know which ones are going to run. I know there are 6 people who are thinking about it. Now, as soon as you are president, you cannot also be vice president, so there will only be 5 possibilities for vice president, and then 4 for treasurer, and then 3 for secretary. So how many different ways can these positions be filled? 6 times 5 times 4 times 3 is 360 different ways. All right, now, if you have a calculator, or if you are just using the formula as it is given to you, and you want to know what that would look like, this would be a 6p4, because there are 6 people to choose from, and they are going to fill 4 different positions. Now, the way it would be set up officially is you would do 6 factorial on top. Remember, that's just where you count down and multiply. And then on bottom, you do 6 minus 4 factorial. Okay. Now let me show you why these turn out to be the exact same answer. Okay. So you've got on top 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. That's what 6 factorial would be if you wrote it out the long way. Now on the bottom, 6 minus 4 is 2. So 2 factorial would just be 2 times 1. So what you would end up with, the top would multiply out to 720, the bottom would multiply out to just give you a plain old 2, and 720 divided by 2 is, guess what, wait for it, 360 ways. So hopefully you can kind of see that there are 2 different ways to do things. So when you look at an example like this right here, 5p3, which is basically our band problem, or 8p2, you have 2 different ways to do these problems, and I don't really care which way you choose. Okay, so for instance, 5p3, if you did it using blanks, you would just say, well, I have 5 different things to choose from. As soon as I choose one, now I only have 4 options, and then I have 3. Okay. If you did the formula, then you would put 5 factorial on top of the fraction, and on the bottom, you would put 5 minus 3, which is 2. And either way, you're going to end up getting the same answer. 5p3, and again, your calculator does it if you just look hard enough. You find out the answer is 60 ways. I sort of prefer the blanks myself, but the calculator is really good if you've got one that gives you what you need to do. All right, what I want you to do, your homework, heaven forbid, now that you've watched the video, thank you for making it this far, I just want you to answer these 2 questions in a comment with your document. So you are going to scan your notes. You're going to show me that you actually did them. And then on the side, I want you to comment with your answers to number 2 and number 3. All right, I hope this helps you get started on your probability chapter. Thanks for watching. Take care of each other. I will see you next time.